This is a great problem that you need to know. First, we have some function. It's a piecewise function, and it says we're going to find the derivative for x less than 1. So we're not going to worry about what happens at 1. So we're dealing with this function, basically f of x equals x squared. So we're going to say the limit as h goes to 0 of f of x plus h, and then x plus h would be x plus h quantity squared minus x squared all over h, which is the limit as h goes to 0 of x squared plus 2xh plus h squared minus x squared all over h. Limit as h goes to 0, we have 2xh plus h squared over h. Simplify that. Can factor out the h and then reduce, and we get 2x plus h. Let's make sure we include our parentheses, and we get 2x. And we've done this problem before. We are not coming in from one particular side because we're finding the general derivative of x squared for all values of x less than 1. And since there's only one equation that works there, that's all you're doing. Similarly, we're going to go to the other side, limit as h goes to 0 of 2 times x plus h minus 2x over h. Again, f of x plus h minus f of x over h. Simplify 2x plus 2h minus 2x over h. 2x's go away. We have 2h over h. That reduces to just 2 because the limit of the function never depends on the value of the function at that point, so we don't care what happens at 0. And this just gives us 2. Now it says to find the limit as x goes to 1 from the left side of f prime. Well, what function are we dealing with? We are dealing with the left side of 1. That's dealing with this first part here. And so that's just going to say 2x, and so the limit is 2. And on the other side, we'll have the limit as x goes to 1 from the positive side of just 2. And since that's a constant, it's 2 as well. Does the limit as x goes to 1 of f prime exist? Yes. It equals 2 because the limit from both sides, the limit from both sides of 1 equal 2, as we just saw in part C and D. Now let's find the left and right hand derivative at 1. So the left hand derivative, now we're doing it at a specific point, so we're no longer using x plus h, we're using a plus h, and a is 1. So we'll have the limit as h goes to 0 from the left side of f of 1 plus h minus f of 1 all over h. And I can do this, start this other part because it's going to be very similar in terms of its setup. And I want to emphasize always what's going on here and what's the difficult part for people. So when we're looking at this, it says f of 1 plus h. If h is going to 0 from the left side, that means it's a negative number. So 1 plus a negative number means it's less than 1. Well, what function's less than 1? We go back and look at our piecewise function. And the one less than 1 is x squared. So we're going to use the x squared for this. And we'll say 1 plus h quantity squared. And we have over h, and we'll have limit as h goes to 0 from the left side. And similarly, when we're on this other one, we'll have plus h, but now we have an 1, so we're going to be using the other function, 2 times the quantity of 1 plus h minus. Now, this is a key part, minus what? It says f of 1. F of 1 is a fixed value. Remember, that is called our anchor point or our fixed point. Which one of these two functions or two pieces is defined at 1? The top one. That's the only one that we can use, and so we can say here f of 1 equals 1 squared, or 1. So on both sides of this, we need to put in 1. It does not matter what's happening on this other piece because it says that 1 plus h is more than 1. That's why we're going to use the function 2x. 1 plus h, in this case where h is going to 0 from the left side, is less than 1. That's why we're using the x squared. But f of 1 is fixed, and so it does not matter. We have to keep that constant. So now we can say 1 plus 2h plus h squared. The rest of it, you can go through the algebra steps. That gives us 2h plus h squared over h. Factor out the h and reduce. We have 2 plus h. Include your parentheses there. And we get 2, just like what we had before. See over here, 2 plus 2h minus 1. Simplify that, 1 plus 2h over h. So we have 1 over h plus 2. Let's include our parentheses. So we have 1 over 0 from the positive side. And what does that go to? That goes to infinity. So this thing is going to infinity. Now the question says, does f prime of 1 exist? A resounding no. Why? Let's look at what's going on. First, the simple reason for why is the left and right hand derivatives. Right hand derivatives are not equal. That's the simple reason. Now let's take a look at a bigger idea here. How come when we found the derivative on the left side, the general derivative for all values less than 1, and we found the general derivative for all values greater than 1, we found those limits, they gave us 2. And the limit as x goes to 1 of f prime exists. Yes, it was 2. Over here we found that one of them, the left side, was 2, but the right side went to infinity. Why didn't they give us the same thing? And at this point, it should be popping in your mind, the limit of a function never depends on the value of the function at that point. This limit here is independent of what's happening exactly at 1. So these values are approaching 2 of the derivatives, but the derivative is a general derivative, not at a specific point. Let's take a look at the graph. I drew it here. And remember, how do we go about doing this? We're doing it at 1. Here's my fixed point. So as I'm coming in here, remember the q positive and q negatives. So this would be a q negative. It's coming through, it's coming around, it's staying there. It's going to a tangent line of 2 as it's coming in from the left side. If we have this fixed point, that right now I'm doing the left and right hand derivatives. So here's a fixed point, and as it's coming in, here's a q positive, and then we'll make q positive getting closer. What are these slopes going to? Those slopes are going to infinity, which is exactly what we found. What if we're not taking into account this specific point, and we're just going to go along our curve and say, what are these slopes going to go to? The slopes will go to, as it's coming in from the left side, they go to this line, and it has a slope of 2. From the right side, it comes in, and this is a constant one. Since it's a line, the slope is constant, the derivative is constant, and it gives us a slope of 2 as well. So we have an equation, or this function, as we come in from both sides of using the derivatives, they both go to a slope of 2. What's the problem, though? Those lines are not the same line. And remember, in order for there to be a tangent line, the limit of the secant lines have to approach the same line, and this is showing they don't approach the same line, which is why the derivative does not exist at 1. You want to know that problem, know those ideas. There's a lot going on in there, but they are important.